So today we're going to move into what's called dynamics. All right, the first section of the course that we just finished was on kinematics. It was essentially how do we describe motion and developing a mathematical model for doing that. Today we're going to start looking at dynamics, which is it's kind of what causes motion, why does motion change in that. Mixing the two together, we get mechanics, the topic of this whole course. So the big question is what causes motion, and the answer essentially boils down to a force. So what is a force? Well, a force, we actually kind of have a good intuitive thoughts on what a force is. It's a push or a pull. If you have some object and it gets pushed or pulled, whatever's doing that is exerting a force on the object. So we need to think about when we're describing forces in a systematic way. There is an object that is experiencing the force, and those forces are applied to that object. They are exerted on that object. That means every force has some agent that is applying the force. So we can think of forces as happening between two things, right? There's the object that experiences the force and the agent that applies it. So if you look at this sort of corny example from the book, if we're looking at the object of the football being thrown, it's experiencing a force that is applied by the agent, the quarterback's arm, and that's going to cause the ball to change the way it's moving in that. So again, forces have two things that must exist for every force. One is the object, the thing experiencing the force, and the agent that is applying the force. Um, Forces are also vectors, right? So we just spent a lot of time describing vectors in our section on kinematics. This is going to build on that. All of the things to do, we learned about vectors, their magnitude, direction, breaking them into components, and that is going to be reoccurring throughout this course. So if you're still struggling with that, or if you're having difficulty, be sure to reach out to me for some help because we need to remedy that. That's not going away. Um, but forces are vectors. They have some magnitude, some size. You can push something very hard, or you can push it softer, and you push them in a given direction. So to fully describe a force, you need, again, the magnitude and the direction of those things. We A very useful thing to do when describing forces is break them into two different sort of cases, right? There are contact forces, forces that you have to be in contact to apply them. So the object and the agent have to be touching for that force to exist, right? So, again, in the photo, there's the ball getting hit by the bat. That bat exerts a force on the ball, but it can only do so if they're actually touching, right? So a lot of forces are classified as contact forces. Um, uh, and it's essentially the object and agent have to be in contact. There are, however, also long range forces. The big one we'll be concerned with in this course is gravity. If you jump off a diving board, you feel a force of gravity pulling you down towards Earth, but you do not have to be in contact with Earth to feel that force. That force can be applied over a long range. So one of the things that'll be very useless, and we'll get to that at the end of useful rather, and we'll get to it at the end of this video, is separating forces into those two classes to help us identify which forces are actually relevant to a situation we're describing. Um, we're going to discuss a lot of different forces. Quick, sort of summary of the ones that we may learn about. Gravity, I just mentioned. Spring forces, essentially, if you take a spring or some other object that can be stretched or compressed, and compress it, it's going to push back on your hand. Tension, if you wrap a rope or tie a wire to something and pull on it, there'll be tension in that rope that would pull the object it's attached to. Something called the normal force, which is a force applied by surfaces and essentially prevents things from going through that surface. Friction, I'm sure most of you have probably heard of before. Drag or air resistance. Thrust, this is how rockets work. And there's also electric and magnetic forces. We're not going to describe in detail electric and magnetic forces in this class. That's in Physics 202, the follow-up course to this. But we'll mention and discuss briefly or in gory detail most of these other forces. And just to sort of quickly give a rundown of what they are, we will revisit these with in a more quantitative way later on. But gravity, gravitational force, essentially any objects that have mass are attracted to each other using due to gravity, and that force is pointed, directly towards the two objects. It's a long range force. We're going to essentially be focusing only on the gravitational force due to Earth or some planet. So when you fall towards the ground or when an object falls towards Earth, that's the gravitational force. It's directed towards the center of the Earth, so it always has that direction. And we'll get into the math in an upcoming video and how to quantitatively describe that. The spring force, I already mentioned. If you compress an object or stretch an object away from its like equilibrium length, we'll call it, that object is going to try and get back to its natural length. So if you compress it, like if I were to take this box and push it that way into the spring's going to push back. So there's going to be a force directed back towards its natural length, pushing on the object. Likewise, if I were to pull the string and make it longer, it's going to try and pull itself back to its natural length, and that force vector would be in that direction. Tension, you tie a rope to an object and pull on it. That rope, provided you don't pull hard enough to break it, is going to essentially pull on the other end of it with the same magnitude of force that you're pulling on the other end of the rope with. The direction of this force is always just in whatever direction the rope is. So in this case, we have a sled with a rope tied to it. If you were to pull that in that direction, the tension would be, the force would be in the direction of that rope. The normal force, this one can actually get, it often confuses a lot of students. I think one of the common misconceptions people think is, oh, it's the opposite of gravity, and that is not true. The normal force is essentially due to the atoms and molecules that make up an object. So in this case, the table, you have all our atoms together held there. If I put something on top of it, that object can't fall through it. So if gravity or some other force starts to push down, these objects will resist that force and push up with whatever magnitude force they have to push up with to prevent that object from sort of penetrating and going into the desk or breaking the surface of whatever the object is. In terms of direction, it's called the normal force. It's actually a math term. So normal, if you recall from calculus, it means perpendicular to the surface. So if I have some flat surface, the normal force is always going to be perpendicular to that surface. And we want to remember that because it's not just, the chair you're sitting on or a table that has a normal force. It's all surfaces can have normal forces. So if you lean against a wall, that wall exerts a normal force perpendicular to the surface of that wall. Likewise, if there's some tilted road or table that something's standing on, that force, there can be a normal force perpendicular to that wall. And again, like all the forces I've mentioned, I'm just really quickly giving you an intro into what they are, and we'll revisit these in more detail as we get through the dynamics section of the course. Friction is another force that can get surprisingly confusing. On one hand, it's really intuitive, but on the other hand, it can have a lot of subtleties to it. So there's several types of friction. The first one is kinetic friction. If you have an object that's sliding on a surface, the friction between those two surfaces is going to want to stop that sliding, right? So that force would always be opposite the direction that the sliding is going on in. The agent is a surface. So again, this is another force that can be applied by a surface. And it's when kinetic friction is when the two objects are moving relative to each other, those two surfaces, and the friction is in the direction that's going to try and stop that motion. And it's always parallel to the surface of that, the surface of the object causing the friction. Static friction, on the other hand, is when the two surfaces are not moving relative to each other. And essentially, that static friction wants to keep those surfaces from sliding. And this can get very confusing, as we'll see, in what that means in terms of direction. So the static friction is going to be in the direction that prevents that object from sliding, and which can be very different for similar looking situations. And when we cover friction in more detail in a couple videos, we'll spend a lot of time, and in our synchronous sessions, going over how to determine the direction of static friction and the magnitudes of that. But essentially, it's the force between two surfaces that's preventing those objects or those two surfaces from sliding relative to each other. Drag or air resistance is a lot of people think it's similar to friction in that there are some differences and everything, but for most problems in this course, we're going to neglect air resistance and drag. It is typically much smaller in magnitude than all the other forces we're worrying about, so it doesn't have a significant effect on how we would describe motion or any forces involved. That said, there is a lab that spends a lot of time discussing drag and that. What it is essentially any object that's moving through a fluid, right? So you can imagine running through air or running through water or moving through any fluid medium. You essentially would have to push that medium out of the way. You'd run into the air molecules or the water molecules, and you would have to push them out of the way. They would push you back, and that force they exert on you is drag or typically air resistance. So you'll cover this more in your labs and that, but you can model this. It depends on how fast you're going and can get very complicated. But we do have ways of sort of dealing with it. It's essentially, if you've ever stuck your hand out the window of a moving car, faster you go, you can feel that air pushing your hand back. It's a contact force with the fluid you're moving through. Thrust, or is essentially how rockets work. We're not going to spend a lot of time on that in this course, but the gist of how it works is it's a contact force with the exhaust of a rocket. And to understand how that works, if you've ever thrown something heavy, so if you've been in a gym and held like a medicine ball, if you throw that ball in one direction, you can feel yourself get pushed in the opposite direction. That's essentially how rockets work. They have a bunch of fuel inside them. They ignite that fuel and essentially throw the exhaust out the back of the rocket really fast. Throwing that mass out the back end causes the rocket to get pushed in the opposite direction. And that's what we call the force of thrust. Again, it can get complicated to analyze quantitatively because the fact that your mass is changing leads to some challenges. But we'll cross that bridge when we get there. The gist is thrust is a contact force with exhaust. It's how rockets work. Throw something out one direction, it pushes you in the opposite direction. Electric and magnetic forces, again, I mentioned this is more for next 202, Physics 202, the next class where we cover E&M. But the forces are treated the exact same way as all the other forces. They're vectors, they have given magnitudes and direction. Just the causes of them are slightly different. You've probably heard, like charges repel and opposite charges attract and things like that. And you're probably all familiar with fridge magnets and things. All of those forces are treated exactly the same as other forces. We're not going to go into the details of how they're covered in this course. But just so you're aware, next semester or whenever you take Physics 202, if you take that, you will learn about these types of forces, and everything we learn in this class still applies. All of the Newton's laws we're going to get into, all of those things, you treat these forces the exact same way. You'll just develop more quantitative models of how to calculate magnitudes and that for these forces. All right, so that was a lightning quick run through of all the forces we're really likely to mention even in this course. What do we do with them? Well, we mentioned they're vectors. So if you recall in kinematics, we describe one of the ways we can describe vectors is in this sort of arrow visual representation. So if I wanted to describe a force, say this tension applied on this box, I would use my particle model, just draw a dot for the box, and I would draw an arrow in the direction of the force. The length of that arrow represents the magnitude. So if I'm pulling really hard, I have a large arrow. If I'm pulling softer, I have a smaller arrow. And the direction is obviously the direction it's pointing. If it was a spring force pushing that box in that direction, it would look very similar, right? I have my particle model, just draw my dot for my box, and I have my arrow in the direction of that force. Typically, we start all the tails of our arrows. We have the arrows start at the object and point in a given direction. And that's how we can visually represent all the forces acting on some object. And typically what we're going to do is we're going to be trying to describe some situation, and we're going to have to pick an object that we want to describe, identify the forces acting on that object, and a very useful tool is what's called the free body diagram, where we draw arrow representations of all the forces acting on that object. And it's, should be pretty familiar to us having with our experience with vectors, how to draw these arrow representations, and we're going to learn we're going to build on how to break them into components and do vector addition and all of those things that we introduced in the kinematics section. The reason that's so useful is because when we're trying to describe how an object's going to move, we want to know the total of all the forces, right? You can imagine if you're sitting somewhere, standing somewhere, and you have two people, say, pushing you in opposite directions, you don't move, right? Even though someone's pushing you to the left, and you don't move to the left because someone else is pushing you to the right, and they can cancel. So the real thing we're going to be concerned with is what's called the net force, or the total force acting on an object. And it's just the addition of all the individual forces acting on the object. So again, when we start to analyze these situations quantitatively, one of the biggest steps in solving those problems and analyzing those situations is being able to identify all the individual forces, determine their magnitudes and directions, and then do this vector addition where we add those all together. And this is called superposition of forces, and it gives us the total force, which will relate to how that object's going to move, right? So if we were to describe, say, some object, some box with a couple ropes on them that people are pulling in different directions, well, if we would draw what's called a free body diagram, we have, some object here, that box, that F1, this force from this rope would be pulling in, say, that direction with that magnitude. F2, the force from this rope here, would be pulling it down. And we would be concerned with the total force acting on that box, which would just be the sum of those two vectors added together. And we know how to do that. This is the parallelogram method, where you put the two forces tail to tail, and the diagonal of that parallelogram is the total force. We can add it using components, all the different ways we learn to add vectors. But the point is, we're going to be concerned with that total force of all the forces acting on that. So the last thing we're going to cover today, which is, has been sort of a quick introduction. So we will revisit this, and we'll go through a lot of examples in our synchronous sessions, is how to identify forces. Remember, the key sort of approach to describing forces on an object and analyzing those situations is going to be adding together all the individual forces. And one of the challenging things to do, or places where a lot of students and people who are new to physics can make mistakes, is making sure we've included every force that's acting on that object, and making sure we haven't included forces that aren't really acting on that object. So identifying these forces is a very important skill we're going to have to work on. And the technique for identifying those forces is broken down very nicely in the textbook. It basically has these steps. The first thing is you need to identify the object you're trying to describe, right? So you identify the object you're trying to describe. Is it that box? Is it this person? Is it whatever it is? And then you want to draw a picture of that situation, including ropes, springs, people pushing stuff, whatever is happening in that situation. Draw a picture of that. Then circle the object that you identified in one as your object of interest. And then this is where separating forces into contact and long range forces can be really useful. You can immediately identify all the possible contact forces by seeing what crosses the boundary of of the object you circled. Anything that crosses that circle can exert a contact force, and you need to think about that in the problem and include it in your forces. Um, when you do that, you've just identified all the contact forces acting on that object. After that, you step back and say, all right, do we have any long range forces? And for 201 in this course, essentially that's going to be, are we on Earth or are we near a planet that has some gravitational force? So a quick example of this is if we have some bungee jumper, right? So, and we want to know the forces acting on the bungee jumper. Well, you draw a picture. They're tied to a rope. They're hanging down like this. That's sort of what's going on. The next, so we've identified our object, the jumper. We've drawn our picture. Next, we would circle that object, right? Now we say, all right, what in our picture, what breaks through that circle? And we can see the only thing that crosses that circle is this rope. So the only thing that can be exerting a contact force is that rope. We know the force exerted by ropes would be tension. So we've identified a tension force that we have to be concerned with in this problem. Nothing else is breaking through that circle. So there's no other contact forces we need to worry about when we're describing this bungee jumper. The last thing we would do is, all right, what about long range forces? Presumably, you're on Earth. So there's going to be a force of gravity, a long range force pulling us down towards Earth. So using this technique, we've clearly identified the two forces that are acting on our bungee jumper, and we're very confident that we're not missing any, and we're very confident we haven't included things that aren't relevant, which may seem straightforward, but as situations get more complicated, you'd be amazed at how often this step is the key mistake that gets made, misidentifying forces or that are acting on the object we're concerned with. So the last thing is let's actually really quickly just walk through a quick example of how to do this. So example, forces on a skier. We have a skier being towed up a snow-covered hill by a tow rope. What forces are exerted on the skier? So in the question, we've already identified our object. We want to describe this skier. So the next thing is, well, let's draw a picture. Well, I have some hill, and then, it doesn't have to be a good picture, but here's my skier. Holding ski poles. There's my skier, and they're being towed by a tow rope up the hill. So that's a rope, right? So that's like I said, you don't have to have a good picture, but a picture of the including everything everything in that situation. So the next thing we do is circle the object we're concerned with, right? So there's my skier. I've circled it. I've circled the object I'm describing. Now I just have to look for what actually breaks through that circle. And well, right here we have the rope. So the force due to a rope is going to be tension. So I've identified tension. I also have the surface of the ground is breaking through that surface. So it's touching a surface. And what forces can be described, or what forces can be exerted by a surface that's in contact with it? Well, we mentioned earlier there's a normal force, so there can be some force perpendicular to that surface. And there's also the potential for a friction force, right? So that surface is in contact with our skier. It can exert contact forces associated with surfaces. So I have to be concerned with those. The circle over here is the same surface, so we've already kind of described that in contact. There's nothing else breaking through this surface. There are no other contact forces we have to worry about. So then we move to the last thing, and are there any long range forces, which again, essentially, is there gravity? And we're on Earth. There is a force of gravity that we are concerned with that's going to be pointing straight down towards Earth. So using that technique from here, we identified our object, we drew a picture, we circled the object, we located everything that crosses through that circle, and named every force for every one of those things that was in contact with our object, and then we named our long range force. And we identified the 4 forces involved in this situation. We should be very confident with that, with doing that, and we're set up to start building our model for how to describe the forces and how this object is going to move in response to them. Again, we'll go through some examples together and discuss this further in our synchronous sessions, and we're going to start to build quantitative models of, okay, now that I know these are the forces involved, what is the magnitude of that gravitational force, and what is the magnitude of tension, and so forth. And we're going to start building Newton's laws from here. If you have any questions, contact me, and I will see you in our synchronous sessions.